Paleontology is usually associated with the vast, sun-baked deserts of the American West. But in 1965, a highway project in central Connecticut revealed something the deserts had missed. While cutting through a sandstone deposit, construction workers cracked open a rock to find a fossil skull measuring barely an inch long. The specimen ended up in the collections of the Yale Peabody Museum, where it sat in a storage drawer for decades, known only by the nickname Stubby. This seemingly insignificant fragment of rock held enough anatomical detail to challenge decades of established history regarding Triassic ecosystems. In the early 1990s, scientists identified the skull as a relative of the modern Tuatara, a rare lizard-like reptile from New Zealand. But the investigation stalled. The skull was too tiny and delicate to handle, and crucial evidence, specifically the teeth, was entirely missing. Traditional tools like hand chisels and dental picks were useless. The most important anatomical structures were trapped deep inside the hard stone matrix. Scientists faced a paradox. To understand how this tiny creature functioned, they had to see inside the stone without destroying a 200-million-year-old artifact. In 2018, a team led by Adam Pritchard used micro-CT scanning to finally penetrate the rock. Using 3D rendering, each bone was digitally extracted, allowing the team to inspect the specimen in virtual space. It revealed a snout reinforced by overlapping bones, built to withstand intense stress. Behind the eyes, massive chambers were dedicated entirely to housing jaw muscles. Measurements of these chambers show that this animal had a bite force that significantly exceeds anything else at this scale, fossil or living. It likely specialized in crushing hard-shelled prey, like beetles or crustaceans. These biomechanical details suggest Stubby was a specialized apex predator, occupying a niche that few other tiny Triassic reptiles could reach. Pritchard's team fed this new anatomical data into a phylogenetic matrix to determine exactly where this predator sat on the family tree. The results contradicted the 1990s consensus. This animal, now named Colobops, shared almost no traits with Tuataras. Instead, it appeared to be a basal Rhynchosaur, an early relative of the lineage that produced crocodiles and dinosaurs. The scan provided enough evidence to move the specimen from the lizard branch and place it among the ancestors of the archosaurs. Science is a process of constant reevaluation. In 2020, a rival study argued that the 2018 model was based on a flawed assumption. They argued the fossil was squashed over millions of years, artificially widening the skull. Digitally uncrushing the model narrowed those massive muscle chambers. It also revealed large eye sockets and a fontanelle gap, traits of an infant, not a specialized predator. This rebuttal placed Colobops right back with the Tuataras, suggesting that high-tech models are only as accurate as our assumptions about the original fossil's condition. This leaves the identity of Colobops at a crossroads. Is it a unique, bone-crushing cousin of the dinosaurs, or is it just a squashed baby Tuatara? The confusion is driven by a phenomenon called conconsurge evolution. This occurs when two unrelated groups of animals independently evolve the same physical traits, like reinforced snouts, to solve the same survival problems. To break this tie, we need more than a computer model. We need to find a second specimen that still has its teeth intact. Until then, Colobops remains a demonstration of how nature can use the same blueprint to fool both 1990s paleontologists and 2018 supercomputers. The story of this 1-inch skull serves as an avatar for the modern scientific method. It shows our tools evolving from hand chisels to micro-CT scanners and complex digital debates over physics and anatomy. Science is never a static list of facts, but an active argument where a single tiny fossil can force us to re-examine how we map the ancestors of all modern reptiles.